All right, in today's lecture, we're going to look at two very important data structures in computer science. One's called a stack, and the other is called a queue. And oops, here's the overview of what we're going to be talking about. So we're going to talk about a little bit of technology, what an abstract data type is, and how that's kind of different from its underlying data structure. And then we're going to spend a lot of time looking at examples and describing the difference between a stack ADT and a queue ADT. And we'll see some example applications of each of these for various things. First of all, what do I mean by abstract data type, or ADT? Well, it's a collection of data and a set of operations on that data. So it's kind of like our definition of a data type, other than we're talking about a collection. We're not talking about an individual object or um, you know, just a single thing. We're talking about a collection of things, and we call it abstract because we like to think about it just in terms of the semantics, like how it works. How do things get added? How do they get removed? And so on. And the basic operations. We don't want to think about the internal workings of it. Just knowing it's a stack ADT should tell us how to operate it, and we shouldn't need to know all those internal details. And some examples of stack or of ADTs are like a stack or a queue. Something you might eventually learn about would be like a symbol table that maps keys to values. We've already seen the list ADT as instantiated by the Java ArrayList object, and it stores a collection of things and it keeps them in order. And there are other ADTs like something like a sorted list, which always keeps things in sorted order. So whenever you add something, it always gets put in sorted order. The differentiation between an abstract data type and a data structure is when we start talking about the data structure, we're actually talking about exactly how it gets implemented in code. And there are often a bunch of different choices. And we'll see in this lecture and the next lecture, a stack ADT could be implemented in any number of different data structures. And the choice of data structures can have impacts on the performance or the memory overhead and things like that. You might implement a stack using an array, or you might use something called a linked list, which we're going to learn about, or there are other kinds of links, more complicated link structures as well. And that's the actual data structure, but it's separate from the concept of the ADT. All right, it's still a stack ADT. It just may be a stack ADT using an array data structure, or a stack ADT using a linked list data structure. So that's the difference there. When we talk about collections, this is a kind of class of different things that can basically store. It stores a collection of things. And today we're going to look a lot about the semantics of how an item is inserted, how an item is removed, all right, and not how it's removed, but which one gets removed. What's the policy when you remove something? Which one is the one that you remove? And then a common operation we're also going to need to do is testing if that collection is empty. And common types of collections would be the lists, so the one we've seen before, the Java array list. And the semantics of removal for a list are you can specify the position. So if you got 10 things in the list, you can remove at any specified position. And in the array list, we saw that with the remove method. So you could call remove with an integer, and that would remove a specific element from the array list. A stack. The removal semantics for a stack is to remove the most recently added one. Okay, last in, first out policy, or a LIFO policy. And this is like the trays in a cafeteria. So as new trays come out of the dishwasher, they just push them onto the top of the stack. And if you were to pop the last one off of that stack, that would be the most recently added one, the one that just came out of the dishwasher and is still wet and warm from the dishwasher. So that's a LIFO policy. The only difference between a stack and a queue is this removal policy. And a queue removes the least recently added, okay, the FIFO, first in, first out policy. And a queue would be the sort of British term. If you're at the grocery store, you'd be waiting in the queue. All right, and you don't want to violate that. Having lived in the UK, you obey the queues there. Trust me. Otherwise, people get very grumpy at you. And we use, in American English, we use the word line for that. You don't get to jump the line or jump the queue. You wait if you just arrived, you're going to be the one waiting there the longest. All right, the person that was least recently added to that queue is the one that gets service next. All right, that is the one that's been waiting the longest. And finally, another very useful collection type in computer science is a symbol table, and this is good at mapping keys to values. And a removal policy for a symbol table would be, remove the item from the symbol table with a given key. All right, and this would be a data type you'd use for things like a phone book, or mapping a name to a phone number, or a domain name to an IP address, or something like that. Let's talk about the stack. This red rectangle represents the current state of our last in, first out stack. And the policy, remember, is always to remove the most recently added. Well, first of all, we got nothing in our red rectangle. And if we were to call the stack ADTs method is empty, it would return true. There's nothing in our stack at this point. Let's say we push a meat pizza onto the stack. And so now our red rectangle contains just that meat pizza. And then we could push a veggie pizza, and the veggie pizza is now on top of it in the stack. And then we could push a cheese pizza. Now, the semantics of the stack, if it's kind of tough cookies. If you want that meat pizza, there's no way to get to the meat pizza without taking a cheese pizza and a veggie pizza for the team. You can't get to the meat pizza until you kind of do your time eating cheese and veggie. Okay, that's life on the stack. All right, if you pop, the first thing you pop is going to return that cheese pizza, and then if you were to pop again, it would return the veggie pizza, and then finally on the third pop you'd get the meat pizza. And here is the API for the stack ADT, and I'm going to call this one stack of strings because it specializes in just storing strings. And you can push a new string onto that stack. You can pop and this should say most recently added string. Okay, this is a bug in the slides. All right. Stacks always remove the most recently added thing, the thing that's been waiting the least amount of time. It just got put there and it gets to go away. It gets to get popped right away. All right, and then it checks if it's empty. And here's an example with strings instead of pizzas. If we've pushed and then we push quick, the state of the stack would look like it does on the left. And if we push brown, that would go on top of there. And then if we were to pop, then the result to pop would be brown, and if we pop again we get the, and if we pop again, this pop would return quick, and then if we popped again we'd get the. Let's use a LIFO stack, last in first out stack, to reverse all the words in a file. And if we're reversing, somebody inputs a string like glory is fleeting but as obscurity is forever, it should output forever is obscurity but fleeting is glory. All right, so it kind of makes sense in both ways, sort of. And our approach here, now we've seen reversal before, and we could do this like we could add all these things to an array list and then go backwards through that array list. But actually a LIFO stack actually provides all the functionality we need, because what we can do is we can read those words in. All right, we read in from standard in, we read in glory, we push glory onto the stack, we push is into the stack, then fleeting, and so on. And when we get done, forever will be on the top of the stack, which is just what we want, because then we can pop and pop and pop and get the words in reverse order. All right. Here is the code, and it's a short and sweet program. Once we have this stack ADT, it's actually easier with the stack ADT than doing something with like an array list, because array list, you gotta find the index and go backwards, and make sure you're not off by 1 and you're going to the right, greater than or equal to 0, and so on. You gotta get all that right. Whereas with a stack, all right, we just create it here, and notice stack of strings doesn't specify, just like an array list has no particular size limit, neither does our stack of strings. All right, we're not even gonna at this point I'm not even gonna show you how stack of string works. Just assume it's a stack ADT, and it's a stack ADT, so it has the operations is empty, it has a push, and it has a pop. All right, and in stackland, adding something to the collection is a push. So this is kind of historical. We always call it push, and often you name the methods push. And removal is always a pop, and that just reminds us that we have this in analogy with a stack of trays. You push things on and then you pop the thing that's been most recently added to it. All right. And here is the the reversal words here, and we could run it. Not terribly exciting, but a quick brown fox. Okay, and hit Control D, and it'll reverse it. That's because we push quick, we push brown, we push fox. And at that point, however this guy is doing his job, and we don't really care, we're just the user of their data type, then we just keep looping. We loop while there's still something on that stack and pop and print it out. Okay, and we get it in reverse order. Let's look at a more interesting example. Let's say we want to check a mathematical expression to see if the parentheses and the square brackets are balanced. And in the first two examples they are. That's because we open a square bracket and then open a parenthesis and open a parenthesis, but we're closing them in the correct order. We close the one parenthesis, we close the other one, then we open another one, then we close it, and then finally we close that first square bracket. So that's all good. All right, as is this other one. All right, these are unbalanced though, because this one, like, all right, we open the same three, then we close the parenthesis, we close the second parenthesis, then we open, okay, that's fine, then we close, and that's fine, but what we're doing is we're missing out on closing that square bracket, and that's an unbalanced mathematical expression. This guy is trying to close this parenthesis here, but it hasn't been opened, so you're not allowed to do that. Okay, and then this one's got several problems. All right, these two parentheses are balanced, this one's balanced, but this one's unbalanced, and furthermore you're missing this square bracket. Somebody's got to close this guy off. All right, you might be thinking, well, this, you could maybe imagine various ways to do this. All right, maybe I should count up how many square brackets I've encountered, opening square brackets, and how many opening parentheses I've encountered, and then I'll decrement it here, and if I get to 0, maybe that'll be a problem. But that's really not going to do the job, because the order is important here. All right, just counting them, how many parentheses or square brackets isn't going to actually do the job. And as you might imagine, right, the proper way to do this is with a stack ADT. And using our stack of strings, we have an algorithm that works as follows. We go through the string looking for the next token. All right, and in all our examples, I'm just going to, for simplicity, everything's going to be separated by white space. If the next token is a open parenthesis or a square parenthesis, open square bracket, I'm going to push it onto the stack. If, on the other hand, I get a closing parenthesis, I'm going to pop the stack, and what I pop better be a open parenthesis, because if it's anything else, that means I've mixed and matched my parentheses and square brackets. Same holds true for closing square bracket. If I see a square bracket, closing square bracket, I'll pop my stack, and then it better be the case that pop value is that opening square bracket. And we're going to ignore all their tokens, so letters, symbols, numbers, all those are just going to be ignored by the algorithm. We're only concerned in this particular example with balancing those parentheses and those square brackets. Here's an example of a correctly balanced, so you can look at this expression and see that our parentheses and square brackets are all balanced. And here's how the algorithm would proceed. It would encounter that square bracket and push onto the stack, encounter that parenthesis and push onto the stack, and encounter that square bracket and push onto the stack. Then it ignores the A, the plus, and the B, and it gets to the closing square bracket. Well, it doesn't push closing things, it pops. It pops, and when it pops, it makes sure that what it pops is an opening square bracket. All right, I'm a close, so the last thing you push better be a open square bracket, and it is. We encounter the next one that's a close, and we pop the stack, and indeed what we pop is this guy here, which is a open parenthesis, so all is good. Now we're building back up, so we kind of went up, and then we back down, and now we're building back up again. We're pushing a open parenthesis, then we pop it, and that matches, and then finally we pop this, and our stack is now completely empty, which means we've got a balanced expression. There's no extra things we've left unclosed. Here's an example of a failure. All right, so look at this and see, What's the problem with this one? Well, there's several problems, right? So this guy's over here, this expression's all good. All right, and when we've got an open square bracket, we need to close that. That's good. The problem is, right, this guy should be a parenthesis. We're trying to close this parenthesis with this square bracket, and it's not matching. Build up would be, push, push, push. Then we pop. That pop is fine. This pop matches. Then we start building up. We do a push, and now we pop. Well, I did get a closing thing, but I got a closing square bracket, and it doesn't match this pop value. And at that point, I could terminate my algorithm and say this is not a balanced expression. Here's another failure mode. What's wrong with this one? Well, so this guy, again, this guy is all balanced. We got this square bracket. All right, we're trying to close too many square brackets here. We've got an extra square bracket, and this will build up as before. So we push, push, push. We pop and we match. We pop and we match. We push. We pop and we match. We pop and we match. That's great. And okay. If we try to pop there, there's nothing in the stack to pop. The stack is empty, and therefore we've got an extra trailing square bracket, and it's not a balanced expression. And this is kind of an abbreviated, so assume we went all the way through there and we were missing these two square brackets, okay, or the single. I guess we need one, right, to close it properly. We've finished our expression. There are no more tokens, and so I would expect at the end of the expression to have an empty stack, but I don't. The stack isn't empty here, and that's also considered a failure of balancing. Here's the algorithm. Here's the first part. So we're going to loop on standard in and read while it's not empty and get a token, the next white space separated token. And whenever we encounter an open parenthesis or open square brackets, we push. Else if the token is a closing parenthesis, so this case only handles the parenthesis case. First of all, check to make sure if the stack is empty and I hit this closing parenthesis, I'm not balanced. All right, that means I've got an extra closer and I don't have an opener. All right, if there is something in there, okay, if it's not empty, then I'm going to go ahead and pop it and see, well, does the value I get equals the opening parenthesis? And remember, always compare strings with equals. Dot equals never, almost never ever equals. And I'm doing it properly here. And if it's not equal, then it's not balanced, and then I bail out. Okay, and return is fatal for this, program. As soon as I do a return, the algorithm is over and it's not going to parse any more data. Similar case for square bracket, just for fun I mixed it up, instead of using dot equals. Another method you could use is compare to, and if you look up the documentation for compare to, you find out it returns an integer, and if that integer is equal to 0, then it's equal. So that's a safe way to do a comparison as well. Just remember, never do you never want to do token equals quote square bracket. That's a bad idea. And same case here. If it's empty, you failed. If it's not empty, then it's going to evaluate the second thing and make sure that what it popped, this essentially checks if it's not equal to what we expect, then we're going to bail out. All right. And then finally, this handles the loop, making sure everything's balanced. But when we get done, there's also that case. We got to make sure the stack is completely empty at the end, and if it is, it's balanced. If we've got some things still that remain unresolved, then it's not balanced. And we can test it out in here's the program in Eclipse, and we can run it, and we can for a plus b, that's balanced. If we plus b plus c, I don't know, plus, okay, and that's all good, except if I forget that closing parenthesis, it's not going to be balanced. All right, and so let's look at a queue example. Remember, queue is just another word for a line, or whoever has been in line the longest is the one that gets serviced. I'm going to represent this by this red rectangle again, and initially there's nothing in it, and if you were to test is empty, you would find out that it is empty and nothing's in there. If we in queue, say these are people waiting in line for tickets to a show or something, We in-queue Abe, and he's now at the front of the line. He was the guy that gets service next. But say that ticket seller is busy right now, and Bill rocks up. Okay, and I guess in Bill's world it's raining. All right, he's got his umbrella and his slicker on. All right, he's waiting behind Abe, and then Carol shows up, and Carol's waiting behind Bill and waiting behind Abe. Okay, now we DQ. Well, who gets to go? Well, fairness dictates that Abe has been waiting the longest, so Abe gets to go, and that's the FIFO first in, first out policy. If we DQ, it's going to return Abe. If we I guess we in-queue. Diana's going on a hike or something, all right, but she needs tickets to the show first, and she shows up, and now she's after. And who gets? If we DQ, who's going to get serviced? Well, it's going to be Bill. He's been waiting longer than Carol, and certainly longer than Diana, who just showed up. And same thing, here's a queue API, and it's queue of strings. It holds a queue of strings, and it has essentially it has the same, three methods. You can add something, you can remove something, and you can check if it's empty. But tradition dictates that we call these methods in-queue and DQ instead of push and pop, or insert and remove. In-queue is adding something to the queue, and DQing is taking something out. And here's an example of strings. We had the quick. All right, if we in-queue something else, it's going to go brown, and assuming the top is sort of the front of the line, if we DQ, the would go, and then quick would go, and then if we DQ'd a third time, brown would go. Here's an example I'm going to show you. When you're talking to kids of a certain age, often, right, you want to prevent them from knowing what you're talking about. For example, you might say something like, after the kids go to sleep, let's have some COOKIES, because you don't want them to know you're going to have cookies, because then they're going to whine and want some cookies, right? But I get sick of spelling, and I decided to write a computer program to do the same thing. All right, I want to be able to type the word cookies like really fast. All right, but I want it to spell out one letter per second, because somebody else maybe has to write it down or something like that. And all right, it is a little contrived example, but it's kind of cute. So I'm going to use the Queue ADT to do this. And queues are good when we have this mismatch of rate. I've got my typing keys arriving very quickly, but I want to do this playing one letter at a time, and maybe the letters take a little while to play, and I want to delay between each one. And I've got to sort of smooth that out. And this is a very common thing you might need in computer science. For example, all the routers, routing all your internet traffic, stuff may arrive at those pieces of hardware really, really quick. And they may not be able to service them all right away. So things have to wait in line. They get queued up in a FIFO queue, and if your packet's been waiting the longest, then you get the next. Then hopefully your web request, gets to proceed through the internet. Here's the program. So I'm going to start by creating an instance of my queue of strings. And again, notice I've got a case I'm not specifying the size. This queue can hopefully hold as many things as I need. Then I'm going to loop and collect letters. All right. Here's my my loop, and I'm going to use standard draw, okay, and check if there's has the key been typed, and if so, get that key. And I'm only going to support A through Z here. And what I do is I in-queue that. Whenever they type a key, I in-queue it. And here's just a trick, right? Key is a char, and I want to add it to in-queue, which takes a type string. So I use kind of a standard trick of an empty string appended, and then append the char onto it. And then it's going to sleep for 100 seconds. All right, and then every time 1,000 seconds, okay, if something's been waiting, not 1,000 seconds, 1,000 milliseconds, so 1 second, it's going to draw that letter and play a wave file. So I've got 26 wave files for all the letters of the alphabet, and it's going to DQ, get to the one that's been waiting the longest, and play it. All right, let's try that out. There it is here, and so I can type cookies really quickly.
COOKIE S.
All right. So I typed it really quickly, but it got, it goes through the queue, and the queue dictates how fast it comes out. So um,
A.
if I type very slowly,
A.
okay, it goes
A.
right away. But if I type A B C D E
A.
F G,
B. C. D. E. F. G.
it spaces them out, and so it's all going via the queue data type. All right, to summarize what we talked about today, we looked at two very important abstract data types in computer science, the first in, first out stack, and the policy there is whoever's been waiting the least amount of time gets to go next. So if you've just been added, you're the one that gets removed right away. This is different from the last in, first out queue, whereas whoever's been waiting the longest in a queue gets to go next and gets removed. And next time we're going to look more at the data structures, and so I haven't even shown you how either the stack or the queue is implemented, and there's a variety of choices, and that's the actual data structure involved in implementing the abstract data type.